equipped classrooms, laboratories with advanced research instruments, library with newest literatures, books, encyclopedias, magazines and journals, student center as the core of students' organizational activities, greenhouse, computer laboratories, fast internet access, sports center, mosque, and gazebo.
Good morning. On behalf of Dean Faculty of Science and Technology, Airlangga University, first of all, I would like to introduce the Faculty of Science and Technology briefly. From 2008, Faculty of Science and Technology have 8 undergraduate study programs. We have around 3,000 students with heterogeneous students from low-level economic class until high-level economic. We also have spirit that Faculty of Science and Technology to become 500 best faculty in the world. Finally, since 2011 until now, our Faculty of Science and Technology became champion and medal in the fight of writing, innovation, and research work in the Airlangga University.
Surabaya is one of the oldest cities in Indonesia, which full of Indonesian historical heritage. Despite its rapid development, which makes Surabaya growing up as the second largest city in Indonesia, the historical heritage in this city are well preserved. In Surabaya, Universitas Airlangga was established. Universitas Airlangga is the second oldest university in Indonesia. Since it was established in 1913, Universitas Airlangga has become the best university in the eastern part of Indonesia, proven by the students' various achievements, both in academic and non-academic field. Universitas Airlangga has expanded to 14 faculties, which located in its 3 main campuses, Campus A, B, and C. One of the faculties is Faculty of Science and Technology, located in Campus C.
Welcome to Faculty of Science and Technology.
Faculty of Science and Technology is an expansion of Faculty of Mathematics and Science Universitas Airlangga, which established since 1982, and in April 10, 2008, it officially became Faculty of Science and Technology. FST has 4 departments, and each of them administers several study programs. Mathematics Department administers Mathematics, Information System and Statistics. Physics Department administers Physics and Biomedical Engineering. Biology Department administers Biology, Environmental Science and Technology, and Biology Master Program. Chemistry Department administers undergraduate and master program of chemistry, and there is also Mathematics and Science postgraduate program, which administered by the faculty.
I'm so proud to be part of FST. As a faculty with national and international standard, FST gives me many facilities to support my academic and non-academic activities such as laboratories, student center, and sports center. Friendly lecturer helped me to broaden my viewpoint so that I can appreciate toward nature and environment. And the important thing that I have many diverse friends from Sabang to Merauke.
The main vision and mission of FST Universitas Airlangga is to become the leader in developing science and technology and to build and develop civilized, moralized, and environmentally friendly society. To actualize that, FSD Universitas Airlangga continues to develop itself to become a better study place and study destination. This is proven by the accredited and certified study programs in FSD, both nationally and internationally.
Hello, my name is Muhammad Hashir bin Fadil. I'm from Malaysia and I'm studying in Management and Science University and I'm taking Bachelor in Forensic Science. So, based on my experience here around a month, I can see the lecturers are more friendly and they'll talkative. And when during the lecture, they like to talk and explain more rather than using the slide, because of I think they're more experienced and knowledgeable.
Hello, hi. My name is Nadia binti Norazam. I came from Malaysia. I'm studying in Management and Science University in Malaysia. I'm taking Bachelor of Forensic Science there. My experience in Faculty of Science and Technology here really have a great moment.
In 2016, FSD also support Universitas Airlangga's target to reach top 500 world-class university by strengthening the learning system and increasing the publications. The excellence of FSD Universitas Airlangga in education, research, and community service is proven not only by the students and lecturers' achievements in national and international competitions and publications, but also reflected by the global networking and collaboration with the industry and other educational institutions in various fields. To support the students' academic and non-academic activities, FSD Universitas Airlangga has some facilities such as fully equipped classrooms, laboratories with advanced research instruments, library with newest literatures, books, encyclopedias, magazines and journals, student center as the core of students' organizational activities, greenhouse, computer laboratories, fast internet access, sports center, mosque, and gazebo.
Morning. On behalf of Dean Faculty of Science and Technology, Airlangga University, first of all, I would like to introduce the Faculty of Science and Technology briefly. From 2008, Faculty of Science and Technology have 8 undergraduate study programs. We have around 3,000 students with heterogeneous students from low-level economic class until high-level economic. We also have spirit that Faculty of Science and Technology to become 500 best faculty in the world. Finally, since 2011 until now, our Faculty of Science and Technology became champion and medal in the fight of writing, innovation, and research work in the Airlangga University.
Surabaya is one of the oldest cities in Indonesia, which full of Indonesian historical heritage. Despite its rapid development, which makes Surabaya growing up as the second largest city in Indonesia, the historical heritage in this city are well preserved. In Surabaya, Universitas Airlangga was established. Universitas Airlangga is the second oldest university in Indonesia. Since it was established in 1913, Universitas Airlangga has become the best university in the eastern part of Indonesia, proven by the students' various achievements, both in academic and non-academic field. Universitas Airlangga has expanded to 14 faculties, which located in its three main campuses, Campus A, B, and C. One of the faculties is Faculty of Science and Technology, located in Campus C.
Welcome to Faculty of Science and Technology.
Faculty of Science and Technology is an expansion of Faculty of Mathematics and Science Universitas Airlangga, which established since 1982, and in April 10, 2008, it officially became Faculty of Science and Technology. FST has 4 departments, and each of them administers several study programs. Mathematics Department administers mathematics, information system and statistics. Physics Department administers physics and biomedical engineering. Biology Department administers biology.
Assalamualaikum. Good morning, Prof. Niza.
Good morning. Assalamualaikum.
Good morning, madam. Good morning, madam.
Good morning, Mr. Safari Prabhu.
Am I audible, madam? Madam, am I audible?
Yes. Yes. Okay. Yes, we will start our webinar, I think.
Okay, everybody, we will start this webinar now. Assalamualaikum warahmatullahi wabarakatuh. The Vice Dean of Faculty of Science and Technology, Universitas Airlangga, Dr. Fatmawati, Mr. Safari Prabhu, PhD, from Sri Venkateswara College of Engineering, India, Dr. Lili Susilawati, from Universitas Airlangga, Indonesia, and also participants of Graph Theory International webinar. Good morning, ladies and gentlemen. My name is Nasrulmila from Department of Mathematics, Universitas Airlangga. It's my pleasure to welcome you here this morning. I'd like to thank you for joining us today for this international webinar on graph theory, which is part of Algebra lecture. For your information, this webinar is also broadcast live on YouTube Matematika UNER Official. Ladies and gentlemen, on this next occasion, let me deliver the agendas of the event today. The first agenda is opening that will be consist of singing national anthem Indonesia Raya and welcome remarks from Faculty of Science and Technology Universitas Airlangga. And the second agenda is the presentations by the speakers and also discussion. And the last agenda is closing. Well, ladies and gentlemen, now may I request all of you to stay seated for national anthem Indonesia Raya. Okay, thank you very much. And now we are going to listen to the opening speech delivered by Dr. Fatmawati on behalf of the Dean of Faculty of Science and Technology, Universitas Airlangga. Ladies and gentlemen, please welcome Dr. Fatmawati.
Okay, do you hear my voice?
Yes.
Okay, thank you. Distinguished speakers, lecturers, students, all guests. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, ladies and gentlemen. First of all, I say Alhamdulillah that at this time we are all in good health and can meet even though virtually. On behalf all of members of the Faculty of Science and Technology, Universitas Airlangga, it gives me a great pleasure to extend my sincere and warm welcome to Safari Prabhu, PhD, from Department of Mathematics, Sri Venkateswara College of Engineering, Sri Perambudur, India, and also the participants of guest lecture. Ladies and gentlemen, the current COVID-19 pandemic is a time that we did not predict before, but we must still have the spirit of working well and producing new innovation. As we are doing now, we can hold a virtual guest lecture. Ladies and gentlemen, this guest lecture is held in collaboration with Airlangga Global Engagement Universitas Airlangga through the video conferencing program with Airlangga University or DECOTA. We hope DECOTA program is beneficial as a means of sharing knowledge with international speakers who are competent in their field. Finally, we wish all the participants having an enjoyable and thought-provoking at this guest lecture. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Dr. Fatmawati. And before we continue our agenda, I invite you to open your camera for photo session. Don't forget to use the virtual background that we provide. Okay. Please open your camera.
Amrina, Ayu.
Next, the second.
Please open your camera. Mas Ahmad Ilda. Nurul Ain.
And the last. Okay, thank you.
Okay, thank you very much. Okay, we are now continuing our meeting to the next agenda. That's to hear the presentations, which will be delivered by Mr. Safari Prabhu, PhD, from Sri Venkateswara College of Engineering, India, and Dr. Lili Susilowati from Universitas Airlangga, Indonesia. The presentations will be moderated by Mr. Ridho Alfarisi. Ladies and gentlemen, please welcome Mr. Ridho Alfarisi.
Thank you, Master of Ceremony, for the time. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, everyone. Thank you for your time joining us today in this webinar. I'm very pleased to welcome to all of you in Graph Theory International webinar. I am Rido Alfarisi as moderator in this webinar. Before we get started, I will read some guidelines for today in this webinar. Okay. Guideline number 1, we divided the webinar into 2 sessions. The first session will be a presentation session, and the second one is Q&A session. And the guideline number 2, if you have questions during presentation and Q&A session, please kindly write in the chat box. Okay, ladies and gentlemen, today we are lucky to have 2 special speakers in graph theory topic, Dr. Safari Prabhu from India and Dr. Lili Susulawati from Indonesia. Good morning, Dr. Safari Prabhu. Can you hear me?
Good morning, sir. Good morning.
Okay. Good morning, Dr. Lili Susulawati. Okay. Can you hear me, Dr. Lili? Okay.
Sorry, my microphone. Good morning. Yes, I hear you.
Okay. Well, ladies and gentlemen, let us start our international webinar today. Before we get started, I will read some curriculum vitae of Dr. Safari Prabhu. Okay, his name Dr. Safari Prabhu or Safari Prabhu PhD from Sri Venkateswara College of Engineering, affiliate to Anna University from India. Research interests Dr. Safari Prabhu in graph theory and its application, data index and topological indices. Maybe it's enough for the CV of Dr. Safari Prabhu. I think we can start the presentation. So please, we have 1 hour for you, Dr. Safari Prabhu, to give presentation. The time is yours.
Thank you.
Yes, sir. Maybe you can share your presentations, Dr. Safari Prabhu. Okay. Okay.
Can you able to hear me?
Yes, sir.
It's not.
It's my PPT visible? My presentation visible?
Yes.
Yes. Okay. Good morning.
Yes,
Good morning to one and all present here. First of all, I thank the God Almighty for giving this opportunity to share some of my research interests with the students and the audience of University of Erlangen and my own students in India. And also I thank the organizers of University of Erlangen. A special thanks to
Okay. Okay. Dr. Safari out of live in the Zoom. I will check in the chat in the participant. Safari Prabhu live. Maybe we can wait the some minutes. Maybe.
I will follow.
for the participant, sorry, Mr. Safari Prabhu have some problem maybe in the Zoom meeting. Maybe we can wait some time, maybe. Okay. Okay.
We still try to join in this Zoom again.
I'm sorry.
Okay.
Am I audible now?
Okay.
Yeah.
Yes.
Yes, sir.
We can hear you.
Yes.
Yes. Yes.
The operator.
Yes.
Yes. Can you hear me, sir? Okay.
Yes. Yes. I can hear you.
Okay. Okay. Can you share
1 second.
your presentation?
Yes.
Okay.
Is my presentation visible?
Yes.
Okay. The topic of the day is graph theory and its application in various fields of science. So before getting into any subject, we need to have a history behind the topic. So let me introduce the history of graph theory with the 7 bridges of Königsberg. So Königsberg is a city containing 4 land areas A, B, C, D with 7 bridges. And the problem is it possible to walk around the city crossing each bridge exactly once? Which means you have to start from any city A or B, C, D. You have to start walking on every bridge exactly once. You have to come back to the same city. A Swiss mathematician Leonhard Euler has arrived a fascinating result in land areas A. Has arrived a fascinating result in 1736 that in order to traverse each bridge exactly once and cover every landmass, the number of bridges considered in the given problem should be even. Thus, the Königsberg bridge problem came into the conclusion it is not possible to solve as it has odd number of bridges. So this theory gave a birth to graph theory by Leonhard Euler. What is a graph? A graph G is a set of vertices called nodes, which are connected by edges called links. Therefore, you can call G is equal to V, comma E, where V represents set of vertices and E represents set of edges. Look at this. There are 6 vertices. The link joining V1 to V6 is named by E1. Similarly, V1 to V2 is E2. Likewise, the other edges are named. So here there are 8 edges and 6 vertices. Basic notions. If an edge E belongs to E of G, is associated with a pair U comma V, where U comma V belongs to V of G, then E is said to connect or join the vertices U and V. The edge E that contains the vertices U and V is said to be incident on each of the vertices. The pair of vertices that are connected by an edge are called adjacent vertices. Let us take this example. We define what is your connection of two vertices, an incident of vertices, and adjacency of vertices. The edge E2 connects V1 and V2. The edge E3 incident with V6 and V5, and the pair V3, V4 are adjacent. So this is how we define the incidence relation, the adjacency relation among the edge and vertices. Loops and parallel edges. So whenever you have a multiple edges between the same pair, we can call that as parallel edges. And whenever we have an edge starting from starting point and end point are one and the same, it's called loop. So here, E1 and E2 are parallel edges, E3 and E4 are normal edges, and E5 is a self loop. degree of a vertex. The degree of a vertex in an undirected graph is the number of edges incident with it, with the exception that the loop at the vertex contributes twice to the degree of the vertex. The degree of the vertex V in G is denoted by dg of V. If the degree of a vertex is 0, then it is called isolated vertex. And if the degree of the vertex is 1, then it is called the pentant vertex. So these are the basic terminologies we require in learning graph theory or in learning any problem, any graph theoretical problem. Now, small delta denotes the minimum degree of the graph and the capital delta denotes the maximum degree of the graph. Look at this example. We have 7 vertices and few edges. V4 is a pendant vertex because its degree is 1. And V7 is the isolated vertex because its degree is 0. The other vertices degrees, degree of V3 is 3 because there are 2 edges incident with it. Degree of V6 is 2. Degree of V4 is 1. And degree of V7 is 0. Types of graphs. A multigraph. A graph which contains some parallel edges is called a multigraph. A pseudograph. A graph in which loops and parallel edges are allowed is called a pseudograph. So the example what we had in the earlier slide is a pseudograph example because it contains both multiple edges and loops. Loop. A simple graph. A graph G has neither a parallel edges nor a loop is called simple graph. And connected graph. A simple graph is said to be connected if there exists a path between every pair of vertices. If there is one pair, at least one pair for which there is no path existing, you can say the graph containing multiple components from 2 to higher number. Directed graph. A directed graph has an ordered pair of vertices linked by edges with the direction associated with each vertex. An undirected graph, the relationship between the vertices is bidirectional and the graph can therefore be traversed in any direction. So unless otherwise the direction is stated, all graphs are undirected. Look at the example for the directed graph. You have direction from V1 to V3 and V2 to V3 and V2 to V1. Undirected graph, there is no direction among the edges. There are some cases where you will have specific direction for some pair of vertices and there is no direction for remaining pair of the vertices. That situation may arise. For example, if you consider there are 4 cities and you have roads joining 4 cities. If there is a maintenance process at one road, in that case, if they have only one directional allowed, that means what? One way. If the double road becomes one way, in that case, you will have a particular road connecting pairs of cities will have a direction and all other roads will have no direction. If you have no direction, it is understood that you can traverse in both the way. If you have direction, you can understand that there is only one direction you can go with. So in that case, there is a directed edge and there is a undirected edge. So in that case, the graph is called multi-graph, which means what? Sorry, mixed graph. In which what? You have a graph with some edges direction and some are undirected. So directed as well as undirected edges containing graph is called mixed graph. Regular graph. A simple graph is said to be regular if the degree of every vertex is same. A regular graph with k degree is called a k regular graph. A simple graph is k regular if small degree, the capital degree, both equal to k. Because there is no classification, that's why. You can see the 2 regular graph. the 3 regular graph, and the 4 regular graph. So these are the examples of regular graphs. Complete graph. A simple graph is said to be complete if every pair of vertices connected by an edge. Thus, a complete graph on n vertices is denoted by kn. The number of edges in the complete graph on n vertices is n into n minus 1 by 2. A simple graph G has n into n minus 1 by 2 edges if and only if G is complete. So you can prove in either way. If G is complete, you will have n into n minus 1 by 2 edges, and a graph containing n into n minus simple graph containing n into n minus 1 by 2 edges, then the graph must be complete. And also it is n minus 1 regular. This is again an if and only if result. A graph is n minus 1 regular if and only if G is complete. K2, K3, and K4. See here, K4 is 3 regular, which means what? N minus 1 regular. Cycle. A cycle is a 2 regular graph, or you can say 2 regular graphs are all cycles. A cycle with n vertices denoted by Cn with n greater than or equal to 3. A cycle is classified as odd cycle or even cycle with respect to the value of n being odd or even respectively. They are odd cycles. These are all even cycles. Bipartite graph. A bipartite graph Kmn has a vertex set partitioned into 2 subsets of order m and n such that no 2 vertices are adjacent within the same subset. Let us have an example and check whether this graph is bipartite. There are 8 vertices, 12 edges. The vertices are numbered with 1 to 8 with different color. I will tell you why I just differentiate with the 2 colors among the vertices. So if possible, you have to partition this vertex set into 2 such that edges, no 2 vertices in the same set having edges. Or you can say, if at all if there is an edge, it must start with one partition and end with the other partition. Let us partition. Collect all the pink color vertices in one set. Collect all the yellow vertices in the other set and name them 1, 3, 5, 7, 2, 4, 6, 8. Now look at the original graph. The 2 is connected to 1, 3, 5. Therefore, you join 1, 3, 5. And 4 is connected to 7, 3, 5. And 6 is connected to 1, 7, 5. Therefore, 6 is connected to 1, 7, and 5. And 4 is connected to 3, 5, 7. Therefore, you connect 3, 5, 7. And 8 is connected to the remaining vertex 1, 3, 7. Now you are able to partition the vertex set of the graph into 2 subsets such that each subset contains an isolated vertices. The first set, if you induce, it is a null graph. Similarly, second set, if you induce, it is a null graph. A null graph is a graph without any edges. So if you induce only the pink color graph, there is no edge between the pink color vertices. Similarly, if you induce the yellow color vertices, there is no edge between the yellow vertices. Therefore, that is again a null graph. So in that way, you can classify the bipartite graph. And there is one powerful theorem for bipartite graph. A graph is bipartite if and only if it has no odd cycle. Look at the original graph. You can see everywhere a even cycle, either a cycle of length 4 or 8 or sometimes 6. There is no odd cycle here. Therefore, you can call this graph as bipartite. Or any graph if you take, if you are able to catch hold of all even cycles, there is no or failure in catching hold of odd cycle, then you can very well declare that graph is bipartite in any graph. Walk. A walk is a finite or infinite sequence of edges which joins a sequence of vertices. A trial. A trial is a walk in which all edges are distinct. A path. A path is a trial in which all vertices and therefore all edges are distinct. Cycle. A cycle in a graph is a non-empty trial with only repeated vertices at the first and last vertices, which means in a cycle, you should not have any vertex repeated and edge repeated. That is what induced cycle. Euler graph. A connected graph G is called Euler graph if there is a closed trial which includes every edge of the graph G. A connected graph G is called Euler graph if there is a closed trial which includes every edge of the graph G. Look at this graph. And is it possible to start from one point, travel along all the edges exactly once, and coming back to the same point? That is what the condition for checking whether the given graph is Euler or not. So you start from one point. Let us start from the point northwest corner most. Go in this direction. Next, you can go there. Come here. Go here. Come here. Go here. Come here. Go here. Go here. And finally, you can end up with the same location. If you are not convinced, I can just trace again. Start from one node. Travel along all the edges exactly once, and you are reaching the same destination. Therefore, you can say this graph is Euler's graph. Here again, there is a powerful theorem. A connected graph G is Euler if and only if all vertices of G are of even degree. So in a graph, if you have no vertex of odd degree, then you can say it is Euler's graph. Application of graph theory in real life. So everything in our world is linked. So I am linked with many people now. As of now, I think 100 participants, around 100 participants. So likewise, everything in our world is linked. The cities are linked by streets, rail, flight networks. Pages on the internet are linked by hyperlinks. The different components of an electronic circuit or computer chip are connected. Scientists, engineers, and many other wants to analyze, understand, and optimize these networks, and this can be done using graph theory. The internet. One of the largest graph in our day-to-day life is our web. The search engine. The web search engine like Google, the websites and pages that are connected in a graph help to rank the website and allows Google to display the best result at the beginning. Social media. In a social network like Facebook, WhatsApp, Messenger, Twitter, Google, LinkedIn, users are connected via large graph. Road network. To develop intelligent transport system, to reduce traffic congestion, to travel faster, to avoid car accidents, we need to analyze the road network, and your graph theory helps you in analyzing your road network. Design of computer chips. To connect million of transistors that connects in the integrated circuit, we use graph theory, in particular the crossing number problem in developing the chips. And many more. Computer network security, GSM mobile phone networks, map coloring, and some more applications of graph theory in science and technology. Few NP complete problems. So what does it mean, NP complete problem? A problem which cannot be solved in polynomial time, which means if you are given with a task, if you are able to find the answer, or if you are able to find the answer with the help of a computer or with some algorithm, and if that algorithm runs in polynomial time, then you can say the problem is polynomially solvable. There are some problems where you cannot solve the problem even with the help of computers, with the help of algorithm running in polynomial time. Those problems are called NP-complete problem. I'm going to explain some of the NP-complete problem, in particular, one fine problem with the in-depth concepts. So these are the few NP-complete problems: metric dimension or resolving set. You can call this metric dimension resolving set a subset or a distance-based problem. Why we call subset and distance-based problem, you can understand it later. Fault tolerant metric dimension is a variation of metric dimension problem. Partition dimension, strong metric dimension, doubly resolving set, vertex cover problem, dominating set and invariance, power domination, and it has application in power engineering, independent set problem, topological indices with respect to chemical graph theory, and the crossing number problem with respect to VLSI layout. So here, some problems are only pure subset problem, and some of them are distance problem, and some of them are both subset and distance problem, and some is counting based problem. You just count the number of crossings. So that is what crossing number problem. How we efficiently can lay out the graph with the minimum number of crossings. See, the crossing number problem can be viewed from planar graph concept. Let me take the first problem, multi-dimensional resolving set. Let me explain in detail, and we have arrived at some of the basic results, and which helps us to find the lower bound for a metric dimension, and that I will explain now. Distance and resolving set. Let V of G of V comma E be a connected graph, and the distance between two vertices U comma V belongs to V of G, denoted by D of U comma V is the length of the shortest UV path in G. Length of the shortest path UV in G. Let W is equal to W1, W2, etc. WK be an ordered subset of V of G. See here we are taking subset, therefore it is called a subset problem. And also to create a vector, we use a distance, therefore it is called distance based subset problem. So W with K vertices. For any V belongs to V of G, the representation of V with respect to W is defined as a K vector. The representation of V with respect to W is equal to distance between V to W1, V to W2, etc. and V to WK, and they are given in an ordered form. So when you have a K number of vertices in your W, you will have your representation as a K tuple. And here, once the code or the representation is defined, the resolving set, the set W is said to be a resolving set if any two vertices U comma V belongs to V of G, satisfying the condition, a representation of U with respect to W is not equal to representation of V with respect to W. That means you take a vertex at V and take a subset W containing K vertices, choose two vertices U and V outside the W, and you must have at least one W in W such that the distance between W to U is not equal to W to V. If this is okay, then you can claim your W as a resolving set, or the cardinality of the W called metric dimension, or the resolving number. So that is how the basic definition of resolving set goes. The basis of G is a resolving set of G with a minimum cardinality, and the metric dimension of G refers to its cardinality denoted by beta of G. An illustration. So look at this illustration. See, by just looking into this illustration, we'll be able to identify the complexity of the problem. And in general, you can say this problem cannot be solved in polynomial time, even if you run an algorithm with the help of a computer. Look at this graph. There are 6 vertices, 7 edges. There are 6 vertices and 7 edges. We wanted to take a subset of the 6 vertices. So what are the possible subsets you can have for this 6 vertex graph? Proper subset, not improper subset. That is empty set and whole set you have to leave out. The remaining subsets, that is, you will have 2 power cardinality of the set minus 2. That is 2 power 6 minus 2. 2 power 6 minus 2. 2 power 6 is going to be 2 power 6. 2 power 5 is 32. Into 2, 64. There are 64 possibilities minus the two sets, that is the improper subsets, that is empty set and the whole set. If you remove those sets, the remaining set is going to be huge in number. Of all these subsets, you will have to select one subset satisfying our condition. With respect to that, if you give a representation, your all vertices must receive distinct representation. That is the problem. Let us first select the vertex marked red, give distance to all other vertices. So from vertex marked red, the distance between the other vertices are 1, 1, 1, 2, 2. Now the graph is not resolved because you have 1 repeating 3 times, 2 repeating 2 times. So therefore you cannot say a singleton can resolve this graph. A single vertex can resolve this graph. Therefore you will have to go for another vertex in any other location. The selection of another vertex is going to be your choice, but the ultimate aim is to get minimum number of vertices in your W. Let us select the second vertex marked green. From that, if you give vertices distance, it is going to be 0, 1, 1, 1 and 2. Now if you look at the graph, the other vertices are resolved, that is received a distinct representation, except the top and the bottom corners. 11, 11, that is 1, 1, 1, 1. So you can say the graph is not resolved because of the repetition 1, 1, 1, 1. Therefore you need to go for another vertex marked blue. So if you give distance to other vertices from the vertex marked blue, you get your 0, 1, 2, 2, 3, 3. Now if you look at the representation, all your representations are distinct. You cannot say two vertices receives the same code or representation. So you found one particular subset among those 2 power 6 minus 2 number of subsets. 2 power 6 minus 2 number of subsets. Now the subset what we have is of cardinality 3. Now the next task is, can I reduce the number of vertices in the subset from 3 to 2 or 2 to 1? Let us go for the another choice of selection of vertices in W. Select the first vertex marked red. From that you give distance 0, 1, 1, 2, 2, 3. So in this case you have 0, 1, 1, 2, 2, 3. There are repetitions 1, 1, 2, 2 repeated. Therefore you cannot claim this one is a resolving set. Choose another vertex marked green. From that if you give distance, you get your 0, 2, 2, 1, 2, 3. So if you see the code or representation of the vertices, they're all distinct. So if you can able to reduce from 3 to 2, that is what this. So the new subset with cardinality 2 resolves the graph G. So in that case, the earlier one you can say simply resolving set, and the later one is minimum resolving set. We are interested in minimizing the number of element in the W. See, in the earlier case, your choice of selection were independent, because if you induce your red and green vertex, there is no connection between them. So if you want to have a connected resolving set, you can have another choice. So this again resolves with the same cardinality 2, but these two vertices are being connected. So in this case, it is minimum as well as connected. So if you impose some condition on the resolving set, you get a conditional resolving set. One of this is connected resolving set. Likewise, independent resolving set, connected resolving set, path resolving set, star resolving set. There are plenty of other variations of resolving set available in the literature. So these are the first one, resolving set, minimum resolving set, and connected resolving set. The concept and its relevance. The structure of a chemical compound can be represented by a labeled graph whose vertex and edge labels specify atoms and bond types respectively. The basic problem in chemistry is to provide a mathematical representation for a set of chemical compound in a way that gives distinct representation to distinct compounds. So in this case, Johnson et al. Have identified this problem as a vital role, in differentiating the chemical compounds in a molecular graph theory. Thus, the graph theoretic interpretation of this problem is to provide a representation for the vertices of the graph in such a way that distinct vertices have distinct representations. This problem of finding unique representation for the vertices of a connected graph has application in computer science also, network discovery and verification. So in the network discovery and verification problem, a query at a vertex B discovers or verifies all edges or non-edges whose endpoints have different distance from B. So initially, in a network verification problem, the graph is known in advance and the goal is to compute a minimum number of queries that verifies all edges or non-edges. This is for the graph known in advance. Sometimes the network verification problem, the graph will not be given in advance. Instead, the code will be given. With respect to the code, you will have to find the links between the vertices. So that is also possible with the help of codings, the distinct representations. So the distinct representations can be generated with the help of your subset of vertices. So this problem has previously been studied as the problem of placing landmarks in graphs or determining the metric dimension of graphs. A basis is the resolving set with minimum cardinality. The cardinality of a basis is called a dimension, and the members of the basis are called landmarks. These are the other terms used in resolving set concept. Applications. Chemistry, I have already explained. Network discovery and verification is over. In the robot navigation. So how the resolving set problem can be used in robot navigation? You consider a space in which some entities are connected by some links, and you have a robot. You give instruction to the robot, start from one node, go to 5 distance likewise. So if you give the instruction, if there are 2 destinations at 5 distance, the robot will get confused where to go because there are 2 destinations at the similar distance ordered. So in that case, what you will have to say? You will have to say the destination with a distinct representation, like, which means you start from this node, and from that node it is this distance, and the other node it is this distance. Likewise, if you give, you can able to uniquely represent every destination to the robot so that the robot will reach the destination without any confusion. So that is how the metric dimension problem can be applied in robot navigation in programming. And sonar and LoRaWAN stations, pattern recognition and image processing, geometrical routing protocols, strategies for mastermind game, and safeguard analysis of a facility. So these are all the well-established applications of metric dimension literature. The concept of resolving set appeared in the literature under the different name as early 1975. Slater called these sets as locating set and reference set. Independently, Harare and Welter discovered this concept as well, but used the term metric basis and metric dimension. And Charton et al. Have called the metric basis as minimum metric basis, as resolving set and minimum resolving set. So Charton used the word resolving set. Harare and Welter used the word metric basis. Slater used the locating set, but all are one and the same. The tools. So whenever we talk about a problem, we just find out, is there any technique in finding the answer in a short span of time? So that is how the entire mathematician work on. Being a mathematician, we should not go by our regular computational method because it takes a lot of time and energy, and sometimes you may not be successful. For example, in NP complete problem. So whenever you take an NP complete problem, you start working with the regular procedure, and definitely you will end up with a tired, or you will end up with a failure, concluding that there is no answer or there is no scope for finding the answer in polynomial time. So for which the mathematician hunt for tools. Is there any specific tool with which you can able to trace out the answer in a short span of time. So that is what your tools and techniques used in mathematics. Neighborhood technique. So we use neighborhood technique for finding the metric dimension of certain class of graphs. For a vertex u of a graph G, the open neighborhood u is n of u, which is equal to set of all v belongs to v of G, with u v being an edge. That is what your open neighborhood. And closed neighborhood is open neighborhood along with u is called your closed neighborhood. Okay, so you just take a vertex u, collect all vertices adjacent to that particular vertex u and call as open neighborhood. And if you include u itself into the set, then that is called closed neighborhood. Next, two distinct vertices u comma v are adjacent planes if the closed neighborhood of u is equal to the closed neighborhood of v. We can call that as a adjacent planes. Similarly, for non-adjacent planes, the open neighborhood of u is equal to the open neighborhood of v. See, neighborhood is understood, from which you are defining another concept called twins. Okay, which means what? If you want to claim two vertices as twin, they both should be connected to same set of vertices. Nobody from the two should have extra links with some other vertex other than u is connected with. So that is what your twin concept. Look at this graph. Adjacent twins. Take two pink vertex, they are adjacent, and these two pink vertices are connected to same set of vertices marked yellow, which means what? The pink vertices having connection with same group, or you can say the neighborhood of first pink vertex is as same as the neighborhood of second pink vertex, and the pink vertices are included in the neighborhood of each vertex. Therefore, you can say this is adjacent twin sets. Here it is not adjacent, therefore it is non-adjacent twin. Therefore it is non-adjacent twin. So with the help of this adjacent twin and non-adjacent twin, we can able to crack our metric dimension problem in a short span of time. Look at here, twin sets. Having defined a twin, let us define what is twin sets. So if you collect the twins in one set, then that is called a twin set. See here, the first one, two pink vertices having connected with same pair of vertices, that is yellow vertices. Therefore, you can call those two vertices as twin set. Moreover, they two are adjacent, therefore it is adjacent twin set. And second one, the set of all yellow vertices connected with the two pink vertices, but they don't have any connection between them. Therefore, it is called non-adjacent twin set. So now next concept is, see, as we declare whether the graph is Euler or not, what do you do? A shortcut. If you want to prove the given graph is Euler or not, or if you want to prove given graph is bipartite or not, there are some theorems, right? If you want to prove the graph is bipartite, you will have to search for odd cycle. If there is an odd cycle, you can say the graph is not bipartite. Similarly, if you want to prove the graph is Eulerian or Euler, you will have to search for a degree of a vertex. If there is any one vertex of degree odd number, then you can say it is not Euler graph. So likewise, you will have to search for a twin set in a graph or twins in a graph in order to compute the metric dimension, or at least the necessary vertex of the metric dimension, lower bound of the metric dimension. Look at the first lemma. If u and v are twins in a connected graph G, then distance between u to x and distance between v to x is same for every x in v of G, but not in u comma v. Which means what? If there is a twin, the twin pair in a graph for G, you omit the twin, you collect all other vertices in W, then these two twin will give a trouble, receiving same representation with respect to all other vertices. So this forces what? This gives you an idea about the mandatory vertex of the resolving set. So whenever you have U and V twins and they satisfy this property, that is distance between U comma X is equal to distance between V comma X for every X belongs to V of G minus U comma V, you can very well say either U or V must be in W, because if you consider your other vertices as W set, all other vertices as W set, your U will receive the same representation and V also will receive the same representation with respect to your capital W. So that is the reason your U or V must be in W. UVW be distinct vertices in a graph G. If UV are twins, VW are twins, and definitely UW are also twin, you can call UVW forms a twin set. Let G be a connected graph with a twin set Ti. In a graph G, there are I twin sets, I ranging from 1 to n. Then your beta of G is going to be greater than or equal to all your twin sets minus n. So this is what the result. And with the help of this result, you can able to catch hold of the lower bound or the necessary vertices in W to resolve G. So if you are able to identify the necessary vertices for a W in resolving your G, then you can easily reach out what is the total multi-dimension of the graph G. And there is one corollary: if U and V be twins in a connected graph G and W resolves G, then U or V is in W. That is what I said earlier. Moreover, if U is in W and V is not in W, then if you remove your U, you can always include your V. That means V is the best replacer of U. You can say U is the best replacer of V, or V is the best replacer of U whenever U or V in W. Let us go for a small graph operation with which you can just see how easily I am getting the multi-dimension for this particular graph. Before getting into multi-dimension of double graph, let me introduce what is double graph. Take a graph V1, V2, V3, V4, 4 vertices, and the same 4 vertex with a dash component, because double graph means you will have to use the graph whatever you have the same copy second time. And now select the vertex of the first graph and check for its adjacency. For example, if you take V2, V2 is adjacent to V1 and V4. Therefore, you will have to join V2 with its image V1 dash and V4 dash. So that is what the definition of double graph. So take a graph V1, V2, V3, V4 with 4 vertex, 4 edge, and take a copy of it, call V1 dash, V2 dash, V3 dash, V4 dash, because that is the image of the first selected graph. And take a vertex of original graph, let us say V2, and that is connected to V1 and V4. Therefore, you will have to join V1, V2 along with V1 dash and V4 dash, its image. Similarly, take another vertex V3, and V3 is again connected to V1 and V4. Therefore, you will have to connect V1 dash and V4 dash with V3. Now, next is V1. If you go by V1, you will have the other component, or in the other way, V2 dash, if you go, you will have to take the edge between V2 dash and V1 and V4. Similarly, V3 dash, V1 and V4. So this is what your double graph. Now you can easily see the metric dimension of this double graph by using twin concept. Look at here, is there any twins? See, initially you had a twin. So if you see this graph, there are twin sets. V2 and V3 are twins because they are adjacent to same pair of vertices V1 and V4. Similarly, V1 and V4 are twins because they are adjacent to same pair of vertices V2 and V3. Similarly, when you take a copy of it, that is also going to contain a twin set. So when you have a double graph operation, the resulting graph also contains twins. That is what the objective here. That is explained in the next graph. Look at here, twin set in double graph. Similarly, you can see from the original graph, the V2 is connected to V1, V4, V1 dash, V4 dash. Now my next V3 is also connected to the same 4 vertices marked in yellow color. So now we can say V2 and V3 are twins because they have same set of vertices connected to them. Next V2 dash is again connected to same set of vertices. The next V3 dash is again connected to same set of vertices. Therefore, what you can do? V2, V3, V2 dash and V3 dash, you can together put into one set and call that as a twin set. And no pair are adjacent, therefore you can say it is non-adjacent twin set. This is one twin set. What about the other pair? Look at your V1. V1 is connected to V2, V3, V2 dash, V3 dash. Similarly, V1 dash is also connected to V2, V3, V2 dash, V3 dash. Similarly, V4 is also connected to V2, V3, V2 dash and V3 dash. And V4 dash is also connected to V2, V3, V2 dash, V3 dash. Therefore, V1, V1 dash, V4, V4 dash together forms another twin set, say twin set 2. So the graph is now classified into 2 partitions. Each of them are twin set. I told you if you compare 2 vertex, definitely one will go into W. So if you compare your V1, V2, V3, V2 dash, V3 dash, and any 2 vertex if you select and they happen to be a twins, therefore one must go to W. So if you keep your V2, compare with your V3, they are twin, therefore take this V3 into W. Keep your V2 and V2 dash, they are twin, therefore take your V2 dash into W. Consider your V2 and V3 dash, they are twin, therefore take this V3 dash into W. Last one vertex can be left in your twin set. So in that case, out of these 4 vertices, 3 of them are mandatory vertex which should be in W. So in that case, your necessary vertex in the twin set 1 is V3, V2 dash and V3 dash. Similarly, for the other twin set, again there are 4 vertices. You select or you fix your V1, compare with all other vertices. Since these 2 are twin, you can push your V1 dash into W, and V4 is a twin, therefore you can push into W. V4 dash is a twin, therefore you can push into W. One vertex, that is V1, can be left. Any one vertex you can just leave outside W. So in that case, there are 2 twin sets, each of cardinality 4. Therefore, you can take 3 among each twin set. Finally, it forms a resolving set. So what is the resolving number for this graph? From the first twin set, 3 vertex, second twin set, 3 vertex. So totally 6 vertex. There are 6 vertices are mandatory vertices out of these 8 vertices in order to resolve this particular double graph. So that is a logic. So we arrived with this theorem. Let G be a graph and D of G be its double graph with the false twin sets K, Tk1, Tk2, etc. Tkr, each of cardinality K1, K2, etc. Kr. Then beta of double graph of G, that is metric dimension of double graph of G, is greater than or equal to n minus r plus summation I runs from 1 to r Ki. So you are going to add all twin set cardinalities and subtract the number of twin sets, because you're allowed to leave one vertex from the twin set, not contributing to W, right? So therefore, if there are n number of twin sets, then you will r number of twin sets, you will have to remove r vertices. So that is what your n minus r. The corollary, if G is a twin free graph, see in the earlier example, I have taken a cycle of length 4. There were 2 twin sets, pink vertices and the yellow vertices were twins. But even if you take a twin free graph, that means what? No 2 vertices will be claimed as a twin in a graph G. Those graph class is called twin free graph. So what is twin free graph? In a twin free graph, you cannot claim no 2 pair as a twin. That is what twin free graph. Even if you take a twin free graph, if you find a double graph operation on that, and the resulting graph is going to be twin graph. So every vertex in your graph G will go have a relationship with the the corresponding image of the second graph and form a twin set. So that is what twin-free graph with metric dimension. Twin-free graph with a multi-dimension. Even when you have a twin-free graph, when you do your double graph operation, the resulting graph contains twin vertices. So that is the logic here. So here you will always have a twin set containing two elements. So in that case, what will happen? Every two vertex, there will be one vertex contributing to W, or every two twin vertex, there will be one vertex contributing to W. One vertex can be left free. So in that case, there will be n vertex in the original G. There will be another n vertex in the image G, or G dash you can say. There are two n vertices in which every vertex have relationship with its image and forms a twin set. So in that case, there will be n twin sets, each of cardinality 2. So that is the logic here. There will be n twin sets, each of cardinality 2. So in that case, every twin set will contribute one vertex to W. Therefore, your W will contain n vertices. That is how we arrive the result. Multi-dimensional double graph of G is n.
Sorry, sir, your present time less than 5 minutes.
Yeah, that's it. That's it. Though.
Okay.
So these are some of the references I have taken for constructing this PPT. These are basic references. Whenever we talk about multi-dimension or any multi-dimension paper, if you take, you will definitely get these papers as reference papers. Thanks. Any questions?
For question in the second session, sir, Q&A session.
Okay.
Okay. Maybe you can wait the Q&A session after the second presenter.
Sure. So in the multi-dimension, there is one more technique I can just elaborate or lay a path for another problem. That problem may be again interesting because it has a very well motivated problem called fault tolerant metric dimension. So here, a metric dimension, you will be collecting a set of vertices from G, and you are going to give representation to other vertices from W and check whether all other vertices apart from W are getting the distinct representation. So that is a metric dimension problem. What is fault tolerant metric dimension is, you suppose if you have a situation of having any one node in the W, that is resolving set, getting fault or failure, it is not able to generate code to other vertices. In that case, definitely you will be having repeated vertices or repeated codes among the vertices if one node fails within the resolving set. So the fault tolerant metric dimension aids in solving this problem. So what is fault tolerant metric dimension? If at all, if there is one node being failed or not able to generate code, still the particular set must be able to give representation to all other vertices. Or in the other way, you can say, for V, the vertex at V, take a subset W. If your selected W is a fault tolerant metric dimension, for any two vertices outside W, there must exist at least two vertices in W. In that earlier case, at least one vertex in W. In the later case, at least two vertex in W, such that the distance between two vertices inside W with the distance between two vertices outside W are at an equal distance. So in that case, if one of them gets failed, the other one will take care of. So this has a very rich motivation. Therefore, the papers on this particular fault tolerant metric dimension comes very often in a reputed journal like Theoretical Computer Science, Applied Mathematics and Computation, Discrete Maths and Discrete Applied Mathematics, etc. All CIQ1 journals. And this problem can also be handled with the help of the spin concept we have done a result, basic result, which gives you the characterization of graph with respect to fault tolerant metric dimension as well as the efficient lower bound for fault tolerant metric dimension. That work we joined with the Professor Sandy Glaser from University of Slovenia, and we made a very wonderful result, and that gives the exactly the lower bound for which the metric dimension can be easily identified. So likewise, you can just extend those this metric dimension along with this twin concept to some other metric dimension variations, say strong metric dimension, doubly resolving set, and other partition dimensions, etc. And that's it. Thank you all.
Thank you, Dr. Safari Prabu. Your presentation very interesting, especially graph theory and its applications and metric dimensions. Okay, ladies and gentlemen, we are going to second presenter. But if you have any question for Dr. Safari Prabu, please write a question in the chat box. Okay, we will move the second presenter is coming from Indonesia. She is Dr. Lili Susulawati. Good morning, Dr. Lili Susulawati. Can you hear me?
Yes. Good morning.
Good morning. Okay. Before we get start the presentation, I will read the curriculum vitae of Dr. Lili Susulawati. Okay. Her name, Dr. Lili Susulawati, the lecturer in Mathematics Department, Universitas Airlangga, Indonesia, and a PhD he got from Universitas Airlangga, and inter-research in metric dimension and various or variant of metric dimension, local metric dimension, and dominant metric dimension. So it's very interesting for me. Okay, I think enough for the curriculum vitae, Dr. Lili Susulawati. Dr. Lili Susulawati, you have 30 minutes for presentation. The time is yours.
Thanks. We do. Okay. I will share my presentation. Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning. First of all, I want to say thanks to Mr. Safari Prabu for his good presentation. Thanks, Mr. Prabu, for your coming in this forum. I think it is our first collaboration, and I hope this collaboration will be continued in the next time.
Sure.
For all participants, thank you for your attending. I think many graph experts in this forum, and I hope there will be future cooperation from this meeting. And okay, let me start my presentation. I will deliver my topic entitled Concept Development of Metric Dimension. In this presentation, I will deliver in the two parts. First, I will present the chart of development process of concept of metric dimension, and the second, I will present the formal definition. So I will start. With this chart. Okay. Yes. For first concept, I will start from what Slater and Harari did in 1975 and 1978 respectively. They help with the concept of basis and dimension in the graph. As we know, graph theory is part of discrete mathematical concept, while the concept of basis and dimension are already known in continuous mathematical concept, such as in Euclidean space, and we studied it in linear algebra. Without losing the essence of its meaning, they can define the basis and dimension of graph. The basis of graph, as in linear algebra, is related to a set such that every two vertices in graph have the distinct representation with respect to the set, and they call it as resolving set. The resolving set with minimum cardinality is called a basis of graph, and the cardinality of basis is called the dimension of graph. They define the representation of vertex with respect to the set by using the concept of distance or metric in the graph. So the cardinality of basis in the graph is called the metric dimension. And in the next concept, we can see the Okamoto did in 2010. He defined the local metric dimension. Okamoto defines the set of vertex such that every two adjacent vertices have a different representation with respect to the set. The set with this property is called a local resolving set, and the local resolving set with minimum cardinality is called the local basis of graph. And the cardinality of local basis of graph is called as local metric dimension of graph. Let's see. From the first and the second concept, we can see that in the first concept, we discussed about a set such that every two vertices have the distinct representation. And the second concept from Okamoto, we discussed about a set such that every two adjacent vertices have the distinct representation with respect to the set. We can see that the main difference between the two concepts is in the phrase of every two vertices and very two adjacent vertices. And then we get the definition of metric dimension and local metric dimension respectively. Okay, from this development process, I mean from basis to local basis or from metric dimension to local metric dimension, we can cut the idea of development. I want to say that from this process can give effect to the future, to the further development. Okay, and okay, from the chart we can see the next concept is strong metric dimension by Sebo and Tanier in 2004. In this concept, they define the resolving set by interval between two vertices, where the interval between two vertices is the sets of vertices in the short path of from two vertices. Okay, and we can see they use the different definition of distance. Yes, and in the next concept, what Brigham in 2003, I mean 2003, did, he defined what the dominant metric dimension. This concept combine dominating set with resolving set. With the same logic as I have said before, this concept developed to the local dominant metric dimension by Umilasari in 2020. And the next concept is fractional metric dimension by Urmukam in 2013. He defined this by using a real valued function. What happened here is same as in dominant metric dimension. This concept developed to local fractional metric dimension by Aisha in 2020. And next concept is adjacent metric dimension by Rodrigues and Vernal in 2013. This concept is similar with concept metric dimension, but Klodvig and Fernau use the distance of two vertices only 0, 1, or 2 for the distance between a vertex to itself, for two adjacent vertices, or for two non-adjacent vertices respectively. And the next concept is multi-set metric dimension by Simanjunta in 2019. Simanjunta using the multi-set to define the representation of vertex with respect to set. And the last concept in my presentation is complement metric dimension by Susurawati in 2019. And I will present in the second part about the formal definition. And in the last book, I think it is for the next future development. Maybe we can do it together. And okay. Next. Okay. In the second part, I will present the formal definition of metric dimension. Okay, in this definition, Mr. Safari was, I think, several definition has been presented by Mr. Safari. For the concept of metric dimension, Mr. Safari already explained in detail. However, here I will emphasize how this concept developed. Okay, for the first definition, metric dimension, the set W subset of Vg is called resolving set if of G if for every two vertices U, V in Vg have the distinct representation with respect to the W, where the representation of vertex V with respect to the W is ordered K tuple, or ordered n tuple in this case. And the entry of ordered n tuple is the distance from to vertex, distance of dv to W1 until dv to Wn. And the resolving set with minimum cardinality is called basis, and the cardinality of basis is called the metric dimension and denoted by dim G. And the next is the local metric dimension with the same definition of representation with respect to the set W. Okamoto defined the local resolving set of G if every two adjacent vertices have the distinct representation with respect to W, and the minimum cardinality of local resolving set is called as local basis, and the cardinality of local basis is called local metric dimension, denoted by dim Lg. The next concept is strong metric dimension. In the concept of strong metric dimension, Sebo and Tanir use the definition of interval between two vertices. The interval between two vertices U and V is denoted by I. UV is a set whose members are all of vertices included in the sorted path UV. A vertex W in G is called as a strong resolver of a pair of UV if V element interval UW or U element interval VW. The set W in Vg with W is not empty set is called as strong resolving set of G if every two vertices in G have a strong resolver in W. the strong resolving set of G with minimal cardinality is called as strong basis of G. And the number of and the cardinality of strong basis of G is called the strong matrix dimension of G, denoted by dim as G. And the next definition is fractional matrix dimension. We start with the resolving neighborhood for every two vertices. For every two vertices U and V of two adjacent vertices, sorry, it is not adjacent, yes. For two vertices U and V of G, the resolving neighborhood of the pair U and V is set of Z such that the distance of Z, the distance between Z and U distinct to distance of Z to V. And the next, Arumugam define the real valued function G from Vg to close interval 1, 0 until 1. And for W, set W, subset of Vg, GW defined by sum of GV for every V element W. Function G is a resolving function of G if G xy more than equal 1 for any two distinct vertices x and y of G. The fractional dimension denoted by dim Fg is given by a minimum of G, where G is the real value, sum of real value of G, GV for every V element in Vj. Okay, Vj. And the next concept is local fractional matrix dimension. The difference is in the two vertices. In this concept, Aisyah used the two vertices, two adjacent vertices. And using the same definition with Arumugam, Aisyah define the local fractional matrix dimension of G, denoted by dim FLG, and defined by dim FLG equal to minimum of GL, where GL is sum of GLV for every V in Vg. Then the concept adjacency matrix dimension, Rodriguez and Fernau define the adjacency matrix dimension and adjacency local matrix dimension by using the distance of the vertices only 1, 0, 1, and 2. And the definition of representation of vertex with respect to the set is the same as in concept in matrix dimension. Yes. Okay. The next concept is complement matrix dimension. Okay. Sociologically define the complement matrix dimension as opposite concept from matrix dimension. Let G be a connected graph of order more than 2, and vertex set is Vg and its set is Eg. The set S subset of Vg is complement resolving set of G if there are two vertices UV in Vg minus S such that U and V have the distinct representation with respect to S. A complement basis of G is complement resolving set. I'm sorry, I think it is there is some fault in this slide. The complement basis of G is the complement resolving set that have maximum cardinality. Then the maximum cardinality of basis is called the complement metric dimension of G, entered by Tim Paris G. And the next is what Simanjunta did in 2019 about multi-set metric dimension. Okay. Let a W is subset of G and V is vertex in G. The representation multiset of V with respect to W, denoted by R and V with respect to W, is defined as a multiset of distance between V and the vertices in W. If the multiset representation of FR to vertices, FR to vertices distinct, so Simanjunta called that W is M resolving set. If G has an M resolving set, then an M resolving set having minimum cardinality is called a multiset basis, and its cardinality is called the multiset dimension of G, denoted by MDG. Otherwise, a set that G has an infinite multiset dimension and denoted by MDG equal to infinity. I think the next concept is the concept that matches the concept of metric dimension and other concept. The first is dominant metric dimension, and the second is dominant local metric dimension. A subset of G is called a dominating set of G if every vertex in Vg minus S is adjacent to a vertex in S. Minimum cardinality among dominating set of G is called a dominating number of G and denoted by gamma G. An order set W, subset of G, is called a dominant resolving set of W if W is resolving set and dominating set. The dominant resolving set with minimum cardinality is called dominant basis, and its cardinality is called dominant metric dimension and denoted by D. Okay, by in the same way, Umilasari defined the local dominant metric dimension, and in this concept, Umilasari defined the dominant local resolving set if W is local resolving set and a dominant set of G. Dominant local resolving set with minimum cardinality is called dominant local basis, and its cardinality is called the dating LG. Okay. Okay. I think we can discuss, or maybe we can join to develop in the future development opportunities and of this concept by using different distance concept. Maybe we can use the Steiner distance or merge the concept of metric dimension with the concept of center, I think. And from this two development model, we can do the same type of development by using the previous process. And I think the important thing that I think is where to find well when we build the definition, the next definition. Okay, it is my reflection, and thanks for your attention. Thanks, Mr. Rido. I think it's all for my presentation.
Yes. Okay, thank you, Dr. Lilik Susawati. Your presentation very interesting in variant of metric dimensions. Okay, ladies and gentlemen, we move to the second session is Q&A session. We have 20 minutes for discussion. Maybe any question for our speakers, Dr. Lili and Dr. Safari. Please write the question in the chat box, or at most 2 questions directly. Maybe you can raise hand in the future in the Zoom meeting. Okay. Okay. We wait the question from participants. Okay. Maybe anybody have question for our speakers? The participants can be raise hands or write the question in the chat box. Okay. Not yet. Okay, we wait. We have 20 minutes. Okay, for discussions. Okay. I'll check the box. Okay. Maybe any question for our speaker? Okay. Okay, Dr. Lily and Dr. Safari, maybe we wait the question from the participants. This topic very interesting with applications, metric dimensions. Okay, not yet. Raise hand. I will check the gallery. Okay. No questions. In chat box, not yet question. Okay. Maybe I have a question for the Dr. Safari, not yet for participant. Maybe a moderator. I will ask some question from a doctor for Dr. Safari. Dr. Safari, I have one question for you. Maybe you can explain the application metric dimension in chemistry. Maybe specific examples, chemistry, a component or molecular. Maybe you have explained detail for the application metric dimension of the chemistry.
Yes, very good. And you have seen the first application of chemistry. Sorry, first application of metric dimension with respect to chemistry in my slide. That is, when you take any molecule, you have basically a molecule containing bonds and atoms. So atoms may be treated as vertices and bonds may be treated as edges. So in that case, every molecule will have certain molecular structure and that can be drawn as a molecular graph. See, our first paper is we solved metric dimension problem for titanium dioxide nanotube, because in the titanium dioxide nanotube, there are a possibility of forming a twin sets. So you can just consider the titanium dioxide nanotube. There will be twin sets happening in the molecular structure in many places with the cardinality 2. So what we have done is we just take those molecular structure and identify the twin sets, and from those twin sets we select the vertex to W, and from the gathered W we start explaining the other vertices receives the distinct representation from the set of vertices. So that is set of atoms of the titanium dioxide nanotube. But here, why this metric dimension can be discussed for molecular structure is, see, whenever you have a molecular structure, one particular atom will be named as something like carbon or something like whatever it may be, nickel or iron or whatever. That type of molecule will be spread everywhere when you take a molecular structure. So if you want to call the particular atom C, if you want to name or if you want to call carbon atom in a molecular structure, there will be many carbon atoms. So which carbon atom you are specific to or you are pointing to? So there will be some difficulty in identifying which carbon atom. Likewise. And moreover, the molecular structure, when you just see, it will give one impact. And after later some time, if you see the molecular structure, it will give some other rotated object, or maybe something the earlier one and the later one may be isomorphic, but your structure will be getting tilted. So in that case, the point where you have identified may not be the point where what you are identified in the next picture. So in that case, it is worth of investigating the atoms of the molecular structure with the distinct representation. So that is the logic behind in discussing the multi-dimension problem in molecular structure. And long back, Johnson is a pharmachemist, and he discussed the problem of finding the distinct representation to the chemical compounds, and he identified the problem in the different way. He did not term or find the problem as multi-dimension, or he come across multi-dimension. He defined the problem in different way. The later, that the Chartan problem and Slater problem and the Harare problem put together considered to be the same problem. So they define the problem in different areas. Independently, they define the problem with their own perspective, their own application. For example, Slater introduced this problem in giving devices for the deduction centers. That is sonar, Lorentz, we say. Safeguard analysis of a facility. So he wanted to identify the location where we can fix the camera like event, and from which every cities or all other entities of the particular network can be monitored. So in that aspect, he defined the problem. Chartan defined the problem in different way. Johnson defined the problem in different way. So put together all problem, when you consolidate all problem, we come to know all problem are one and the same. We can say that is a multi-dimension problem. So this is how Chartan explained its own application, Slater explained its own application, Raghavacharya explained its own application, and Johnson explained the application in terms of chemistry. There are a lot of papers you can see a multi-dimension problem solved for chemical class, all ACE problems. The basic motivation is given by Johnson. Okay. He's a pharmachemist.
Chemistry. Okay. Thank you, Dr. Safari. Your answer is very clear for me. Maybe I will read the Johnson paper. Okay. Yes. Thank you, Dr. Safari, for the answer. Okay. For other participant, maybe you have a question for our speaker, Dr. Lily and Dr. Safari. You can raise hands on, or you write the question in the chat box. Maybe I will check in the chat box, not yet question. Maybe all participants is understand. Maybe Ina.
Yes.
Okay. Thank you, Miss Ina.
Yes. My name Ina is from Universitas Erlangga.
Oh.
Okay. It is very interesting if their concept metric complement, complement metric dimension or metric dimension can be related to the concept of the algebraic structure. To Miss Lily, maybe you can explain that you have see but that the relation of complement metric dimension with the concept of algebraic structure like center, zero diffuser element, or and so on.
Okay. Okay. Thank Mrs. Ina Kusandari. Okay. I think I don't think the relation between complement dimension with the concept in algebra yet. But if we discuss about the relation of metric dimension and in algebra in this graph, we can see that about the basis in linear algebra is the set with minimum cardinality such that every element in vector space can be distinguished by the basis. By the basis by using the linear combination. But in the graph theory, basis is the set such that every vertex in the graph can be distinguished by the set by using the representation of this vertex to the basis, and the representation of the set, the vertex to the set is order and tuple. It is the difference between the concept basis in linear algebra and in the graph theory. But the essence of meaning is the same. This set in the two concepts is the set can be distinguished. Every vertex, every element in the vector space or in the vertex of graph. I think it is the relation of concept basis in linear algebra and in graph theory. But why I construct the complement matrix dimension? Because I have the motivation for complement matrix dimension. If the concept of matrix dimension applies a set such that its vertex in the graph can be distinguished by the set, then the opposite concept is that a set ensuring at least two vertices that are regarded the same by the set. Such set is called complementary solving set, and the maximum cardinality of the complementary solving set is called complement matrix dimension. And in the concept of matrix dimension, we choose the minimum cardinality of the solving set. But in complementary solving set, we choose the maximum cardinality. I think it is the opposite concept.
Yes.
Why the concept? I think the concept is used to solve some problem. One of the problem is like this. The concept of complementary dimension can be utilized to formulate problems within a project. There is a project that requires a team of working along with the project leader. In the project, there are at least 2 persons who can be selected as project leaders with the criteria of the two having similar views on the worker team. This is done so that if one of the project leaders is absent, then there is a replacement of project leaders who has similar perspective on the worker team, so that the project can still run well. Okay. And the more worker teams that the project leader can recognize equally, the better, as more people can be prepared as a team. When we interpreted it in the graph, people are interpreted as vertex, and two connected vertices if 2 persons know each other. But I think it is my motivation when construct the concept of complementary dimension, Ms. Ina.
Okay, thank you, Mr. Lili. Maybe we can work together in the reason that algebraic structure. Okay.
Yes.
Okay. Thank you, Ms. Ina. Okay. We have 2 questions in the chat box. Maybe I will choose 2 questions from Mr. Marsudi and Ms. Yuhani. Okay, the first question in chat box from Mr. Marsudi from Universitas Brawijaya. Okay. The question for Dr. Safari Prabu.
Yeah, it's for me.
Okay. Can the concept of twin graph be developed on the graph obtained from the combination of two graphs, sir?
No.
Maybe you can answer. Okay.
Yeah. See, the concept of twin graph is not developed from combination of two graph as I discussed the double graph operation. So if you see the complete bipartite graph, see when you learn complete bipartite graph, at that time you may not be knowing it is also actually a twin graph. So what is complete bipartite graph? You will have a two vertex set and you will have edge between every vertex of x to every vertex of y. So in that case, what you will have, all your x set will have adjacency with respect to y set and all your y set will have adjacency with respect to x set. So complete bipartite graph is itself a twin graph. So it is not that you have to take two graphs and then do a double graph operation or any graph operation and try to form your twin graph. So there are some graph classes already existing in the literature. They happen to be twin graph. And second thing, to identify your metric dimension using your twin concept, your graph need not be a twin graph. You need to have a twins in the particular graph somewhere. Not necessarily all vertices are twins. So what do you mean by twin graph? Twin graph is a graph in which all vertices are happen to be twins. Am I clear? So the first questionnaire.
Mr. Marsudi, clear?
Okay, clear. Thanks.
Yes, sir. Okay. Okay, Dr. Safari, for the second question.
Yes, one
from
second.
Miss Yuhani of UMP. Okay, the question about twin graph, which the concept is approximately like isomorphism concept. Based on your experience, Dr. Safari, are these two concepts equivalent and can be implemented on the same application? Thank you.
No. See, isomorphism on graph is different with respect to this twin concept. Not all twin graphs are isomorphic. Not all twin graphs are isomorphic. And second thing, isomorphic means what? See, there are some graphs which are not basically twin graph, which may be isomorphic to another graph. So whenever I say a graph is isomorphic to another graph, if one graph there is no twin, and definitely the isomorphic graph, other graph also will not contain a twin. See, how do you check your isomorphism, or how do you compare the two graphs are isomorphic or not? You will just go for the degree sequence or the adjacency relation between the vertices and the edges, etc. So when you have your one particular graph without any twin and another graph cannot have a twin, or another graph you claim as isomorphic graph to the original graph may contain twin. So this is different and the twin concept is different. Maybe you will have a graph with a certain twin set and there will be another graph with the same twin set satisfying the conditions of isomorphism. You can call those two graphs are isomorphic. Shia, am I answered your question?
Okay. Okay, thank you, Dr. Safari. Ms. Yuhani, your question is clear. Okay. Okay. For other participants, we have 10 minutes for the Q&A session. Maybe you have some question for the two our speaker, Dr. Lily and Dr. Safari. Okay. Okay, we wait until. Okay. If there are not a question, maybe we can close off these sessions. Okay. For participants, any questions? Okay. If not yet the question for to our speaker.
There is one
I
question
will.
more, Mr. Ridho.
Oh, Miss Mila. Okay.
No, this is from Sigit Pancahayani.
Oh, Sigit Panca.
In
Okay.
chat.
I will check in chat box. Okay. The third question from Sigit Pancahayani to both presenters, this Dr. Lily and Dr. Safari. Is it possible to implement the concept of finding out the metric dimension of twin graph in directed graph? As we know that the dimension of directed graph could be found if it is strongly directed. Thank you. Maybe Dr. Safari or Dr. Lily, you can answer the question from Sigit Pancahayani.
Yes, metric dimension of directed graph is again NP complete problem. It is of great interest with respect to finding metric dimension of a directed graph. But as far as twin concept is concerned, you will have to have adjacency relationship between a pair of vertices in which you will have the same direction. For example, if you have U and V claimed to be twins, you should have directional adjacency between the vertices. The same directional adjacency should be preserved for the V vertex also. So you can just define another definition, that is twins in a directed graph. Namely, if U and V are directed twins, then U and V should be adjacent to same set of vertex with the same direction. So in that case, if you are able to identify the twins in the directed graph, then it will be easy to compute your metric dimension of the directed graph using twin graphs or twin sets.
Okay, maybe Dr. Lily, can you add the?
Okay, I think it is good question, and that is a good idea to develop further, because your question is an idea for further development concept. I think we can do it for the next concept. Thank you.
Okay. Okay. The third question is clear. Okay. Okay. Thank you, Dr. Safari and Dr. Lily and Mr. Sigit Pancahayani. Okay. We have 5 minutes for the Q&A session. You can write the question in the chat box or raise hands. Okay, we wait 5 minutes again. Okay. Okay. Maybe I have some question for Dr. Safari. I interest in lower bound metric dimensions of double graph. Maybe can you found the upper bound of the metric dimension of double graph, sir?
Upper bound on?
Yeah.
See, already there is upper bound, but here a twin concept gives you the necessary vertices. So whenever we say necessary part, and it is happen to be a lower bound.
Okay.
And sufficiency, you can just select some pair and you can identify, or you can take the subset with the cardinality of necessary vertex and exhibit that set as a resolving set or the count as a metric dimension.
Okay.
But for sufficiency, you would be taking a set of vertices with the lower bound cardinality and then claiming that is the resolving set. And there are some other upper bounds available in the literature, but that upper bounds are just vague upper bounds. Using twin concept, you cannot find an upper bound. You can find the lower bound.
Okay.
And you can also characterize graphs. That is another interesting problem. You can just march towards. That is the twin vertices are the count of twin vertices. The number of twin vertices happen to be the upper bound for certain class of graphs. For example, if you take a twin graph, as I said earlier, if you take a twin graph, the fault tolerant metric dimension of the twin graph is the vertex at cardinality itself. So that is what the characterization we did with Sandy classes. So whenever you take a graph, which happen to be a twin graph of order n vertices, the fault tolerant metric dimension is n itself. So in that case, upper bound, lower bound, both coincides. So likewise, you can also characterize the graph in which your twin vertices or the collection of twin vertices or the number of twin vertices as the upper bound for the graph considered. But in general, you cannot say. In general, for normal graphs, apart from twin graphs, you cannot come to a conclusion that only twin vertices are claimed to be the upper bound. They are just necessary vertices, therefore it happened to be a lower bound.
Thank you, sir. Okay, we have 2 minutes for the Q&A sessions. Any questions for 2 minutes? Okay, maybe for 2 minutes, I will read the concluding remark to our speaker. Maybe from Dr. Safari and Lily Sulsawati explained about the graph theory and its application, especially metric dimension and the variant of metric dimension with a parameter local, fractional, and dominating set combined with metric dimension and the complement and fractional, local fractional. And from Dr. Safari, we know that family of graph may be a twin graph and a double graph. We know the new knowledge in graph theory. We family graph and the other topic in metric dimensions. So I think it is not for today for the presentation and Q&A session. Thank you for Dr. Safari Prabu and Dr. Lily Suslawati for your presentation. Very interesting, very good. I'm happy. Maybe all participants are very happy in our webinars with new knowledge in graph theory and its application and the variant of metric dimension. Hopefully, we can get a new value knowledge that we can be a productive person in research. Maybe we can create a new paper with new idea, new research in the future. We can publish in the reputable journal, international journal, and index-based corpus of science. So we hope all participants can be a productive persons in research, graph theory, and other mathematics maybe with application. Okay, I'm sorry if I have some mistake during this discussion. And finally, wassalamualaikum warahmatullahi wabarakatuh. I will give it back to Master of Ceremony, and Master of Ceremony, time is yours.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much for Dr. Safari Prabu and Dr. Lily Susilawati for the interesting presentations, and also for Mr. Ridho Al-Farisi who had moderated this webinar. There are many questions from participants. Is it allowed for the participants to get the copy of the presentation? Miss Lily
sure.
and yes, sir. Okay, so we will share from the chat box. Okay, thank you very much. Well, ladies and gentlemen, we have had productive and inspiring time together, and this event about to come to the end. For all the participants, please kindly fill the absence and write your name clearly because it will be used for a certificate, and we will deliver your certificate by email after this webinar. I also hope you fill the evaluation form that had been shared in the chat box. We'll give you some time maybe to fill it. We can wait about 2 or 1 minutes. You can fill the evaluation form, and you also can fill the evaluation form after this webinar. Okay, we will wait about 1 or 2 minutes maybe while we share the presentation. Okay.
Is it okay? Got the PPT?
Wait.
Milla, I share the PPT.
Oh, yes? Okay, thank you. Thank you, sir.
Thank you, sir. Dr. Safari. I have downloaded your file. I will share it. Sorry.
Everyone. Okay. Okay, there is some problem. So the form evaluation form will be sent maybe while we send your certificate by email because we still don't have the link. Okay, now ladies and gentlemen, I hope you found the presentations of this webinar are informative and helpful. Thank you, and thank you very much. And before we part, please accept this verse from us. Kalau ada jarum yang patah, jangan disimpan di dalam peti. Kalau ada silap dan salah, harap sudi maafkan kami. Which roughly means, please forgive us for our shortcomings. Till we meet again, perhaps in the next webinar. May we always be healthy. And Assalamualaikum warahmatullahi wabarakatuh. Thank you for all.
Waalaikumsalam.